So, before we close this topic on PN junction diodes, let us just look at some of the non-idealities. Okay. So, it is not, if you look at a perfectly ideal PN junction diode, it would be the way we defined it to be, but there are some non-idealities. Okay. So, first we look at the non-idealities in reverse bias. Okay. I am not sure if that is all very clear, but I will write it out. So, reverse bias non-idealities. So, the first one is something called as the avalanche breakdown, which is to say that it is not that the PN junction can keep operating with the same current voltage characteristics for an infinitely large negative voltage. There is a large enough, there is a voltage, okay, which is, so this is when I apply an increasing reverse bias, VA keeps getting more and more negative. So, it is, so far what our equations tell us is that the PN junction would continue having a current that is exponentially dependent and continue increasing in magnitude in a very small manner based on that function, but that is not really true. You will reach a point where the electric field due to the band bending, see the electric field, the bending keeps increasing as you apply the reverse bias, right. It gets, the band bending gets steeper and steeper, and there will be a point where the electric field is so large that the electron drift becomes so large that the electrons can now start colliding with the other silicon atoms and pull free electrons out from those silicon atoms. Okay. So, this is, and this leads to a multiplication effect. You have one electron, you know, getting another electron out, and then these would in turn start pulling out more and more electrons because of this very high electric field, and therefore you have this avalanche of electrons that start adding to the current, and you will find that there is a massive surge in the current and the device simply cannot take that surge and it simply breaks down. Okay. So, this is a purely drift based mechanism, but you have a large, your electron population increases dramatically because of this breakdown phenomenon, and therefore the breakdown voltage, okay, the voltage at which this happens, what is the VA at which this happens? The VA at which that happens is defined in terms of the electric field that is needed to break the semiconductor down. So, at VA equal to VBR, you find that, you know, using your regular expression of electric field, and if you write your electric field in terms of the built in potential, you have this expression, and therefore your breakdown voltage is simply given by this term where the electric field is now large enough to create a breakdown, and therefore if you write these expressions in this manner, you find that the breakdown voltage is inversely proportional to the dopant concentrations. So, if I dope it very large, the breakdown voltage decreases. The third point is something called as is a third non-ideality, is defined, is related to the generation of carriers in the depletion region. Okay. So, in a reverse biased PN junction, your depletion region is quite large and it is quite strongly depleted, okay, with there being no diffusion current and there being a drift current due to the electrons and holes. And so in this depletion region, if you look at the equilibrium condition in a semiconductor, your NP is always Ni square. So, that is your mass action law, but since this region is now depleted, okay, your NP is less than Ni square, which means that if you go back to the recombination generation mechanisms we looked at, if you look at the rate of recombination and generation, this implies that it is going to prefer generating carriers as compared to recombining carriers. In some sense, you have altered, by depleting this PN junction, you have altered this balance of generation and recombination of carriers, and you have encouraged generation a bit more than recombination. That is, the carriers will effectively, you will be generating carriers in a heavily depleted heavily reverse biased PN junction diode. And whatever carriers are generated here, so let us say you generate an electron and a hole, this electron would quickly run downhill to the other side and the hole will quickly run uphill to the other side. And this mechanism is the key between the key to the operation of something called as a photodiode. Okay. So, if you want to sense light, okay, particularly low levels of light, what we do is we reverse bias the PN junction diode. Okay. So, you apply a very huge reverse bias voltage, and when light falls on this junction, you create electron hole pairs, okay, and this electron hole pair creation is encouraged and the recombination is now going to be quite low, and these electron hole pairs now quickly drift to the other side because of this large electric field, and therefore you can collect these electrons and holes and you have a current that depends upon the amount of light you throw in. Okay, so, if you were to actually throw in light, the curve would actually shift, you will offset the PN junction curve a little by adding more because of the generation of carriers. And therefore, this generation of carriers, okay, if it has a certain generation rate G, okay, it would create an effective current, and that effective current is simply G dx integrated from minus xtn to minus xdp to xtn, which is basically telling you that it is the total generated carriers in this region times the area times Q, which is basically a drift component to the excess carriers generated. Okay, so, that is the excess current that you would create because of generation. And in a heavily depleted region, we already know what the generation rate is. If you look at if you go back to the topic on recombination and generation, you will find that we looked at one special case, which is recombination and generation mechanisms in a heavily depleted region, and we find that the generation rate is given by this particular term. And therefore, the total current in a PN junction diode, after taking into account your generation recombination the generation of carriers in the depletion region, in reverse bias, if you include this non-ideality, the total current is not only the current due to due to the exponential dependence of the voltage, but it is also due to the generated carriers, and this current adds on to the current due to the diffusive component of the current. Okay. So, now what are the non-idealities in forward bias? Okay, in forward bias, the first thing to notice is that the currents are going to be quite large. Okay, the currents are quite large, and because the currents are large, you do have an exponential climb initially, but then because of the series resistance or because of any voltage drops in the PN junction diode, okay, if you remember the equivalent circuit of the PN junction, it had a diffusion capacitance, a depletion capacitance, and a diode resistance as well as a series resistance due to the bulk regions and the contacts they make with the metal, etc. And if the currents are quite large, it can lead to a voltage drop across the series resistance, which will effectively imply that the diode is seeing a much smaller voltage. Okay. And that phenomena has to be taken into account, and it will lead to a saturation in the diode characteristics. So, the diode current would look a bit like this. This is the logarithm of the current versus the voltage. So, initially you would see a slope of 1, and then slowly the slope will start tailoring down because of these effects. And this is all taken care of by adding something called as an ideality factor to the equation. So, ideally your PN junction relation had a term like this. It was QVA by KT minus 1, but then in order to account for all this, we sort of tune down this exponential by adding a factor here. Okay, so, this is a real number that you just add in the denominator, and this n is something called as an ideality factor. It can be used to empirically model any such behavior in the p-n junction. So, if n is equal to 1, then it is behaving like a perfectly ideal diode. If n is greater than 1, then there are other effects that are sort of damping the current in the diode. Now, the second non-ideality in forward bias is clearly the opposite of what happens in the depletion region as in reverse bias. Okay. So, it is the opposite of that, which is in reverse bias the depletion region saw an encouraging of generation mechanisms as compared to recombination. But in forward bias the NP product in the depletion region is much greater than Ni square, and therefore recombination is encouraged as compared to carrier generation. Okay. And therefore, if you take into account the recombination, this will contribute to a current. Okay. And the recombination current is essentially given by this term here. Okay. You have a recombination rate and then you have your continued diffusive component. And since you have excess recombination, a diode in forward bias is something that is used to build your light emitting diodes, for example, because you have excess recombination and therefore you have emission of light if you choose the materials carefully. And the final non-ideality, which we have not treated at all in this course, is as to what happens under very large forward bias. When VA is extremely large, you have a large number of carriers diffusing through, and the continuity equation we used is not sufficient to handle that. Okay. So, the continuity equation we used was delta Pn by dx square is equal to delta Pn by tau. Okay. So, this equation is valid only under something called as a low level injection approximation. Now, if you have a very large VA, we have a high level of injection and therefore these equations need to be modified, or you need to have a more thorough analysis of the situation, and therefore you can't assume many things that we assumed in this case. So, particularly this particular term for recombination cannot hold true if you have very high level injection. So, these are some non-idealities that you must be aware of on over all the p-n junction theory we have looked at in this class. With that, we will conclude our analysis of p-n junction.